So thank you very much for having me here. It's actually a super nice conference. And I should admit that I feel a bit of pressure after an amazing talk as the one before, but I will do my best to try to hook you up on the topic and to entertain you. I should give a disclaimer. This is a theory talk. I will not talk about a real experiment, but our theoretical efforts to propose quantum simulator of the sine-Gordon field theory on an actual quantum gas microscope. Okay, so when I received the email for this conference, I've been really recommended of how's it going, like this. I was really recommended to give a broad introductory talk to everybody, PhDs and people working on a lot of different contexts. So I tried to start with something on which we can relate all together. Cats. Everybody likes cats. They of course comes in a lot of different shapes and sizes and so on. But if we're interested only in understanding some coarse-graining behavior, if you want, we can idealize the model and look at a certain theory idealization. Now, of course, drawing a picture is easy, but from time to time in physical models, it can be extremely hard. The theory itself can be extremely complicated. But of course, like we could be just interested in some features, so the theory is nice to describe the small house cat, the tiger, and the lion. But of course, it would be too much simplistic assuming that these guys here are the same, because in everyday experience, where we know that cats are nice, easy to befriend, but I do not know if you ever tried to pet a lion. It's not that easy. So the idea is, of course, we could try to take advantage of this and start with a simple model, the cat that we know how to handle, we can do stuff, and instead of solving the theory, we can use the physical model, the cat, to understand the behaviors of more difficult models to be handled. In this case, the example of the lion. This is the idea behind the analog quantum or cat simulator in this case. Of course, I don't want to talk about cats for the whole talk, so let me jump to what I actually will discuss. We're going to deal with relativistic field theory. Seems like a fancy model. Actually, it's a model I like personally very much. That is the sine-Gordon field theory. It is, you see the Milton in the slides. You don't really care about the parameters. I will tell you more later. It's just a theory for a scalar field, phi just the conjugate field, that is interacting through a cosine potential. This model is actually everywhere. There are a lot of different physical implementations, mainly in 1D. These are one-dimensional field theory, but there are also some materials in more dimensions that behave effectively as 1D systems. You can find it in cold atoms, Johnson junctions, spin chains, pyrimidines to the material, and so on and so forth. And it's quite nice because all of these models, this complicated model, in some approximation, using low energy approximation, are described by the same field theory. The point is that this field theory is very complicated and very difficult because it's strongly interacting. And so you can understand what I want to do now and also how the arrows are going. I want to build to understand a physical model to behave, engineers this theory, and try to see if we can use it for getting actually quantitative results. This actually is not my idea, this has already been done, but there's a problem, and this is the following. I haven't really told you if this field theory is a quantum field theory or a classical field theory. I can also write down a classical model, and that would be a meaningful field theory. And the fact that the current quantum simulators for this field theory actually move in a regime that is very close to the semiclassical limit. So you're doing really a lot of efforts, they're super nice experiments, but they do really a lot of efforts to study something that can be quite well described by classical physics. In the topic of today, we want to build a quantum simulator that works deeply in the quantum regime of the field theory. And this is my task for today. First of all, how do we get sine-Gordon? There are different ways to get it. I will just introduce how we're going to get in the end. Okay, I will tailor a bit of the introduction. So we want to look at one-dimensional effective field theory. So the first thing that we need to do is to, instead of having a two-dimensional system, try to confine it to an effective one-dimensional model. Have in mind what is done in cold atoms with optical lattices or atom chips. Essentially, you start with a ball, a potato, you squeeze it in one dimension, and effectively the atoms will start moving in one dimension, and one-dimensional physics will emerge. This is not sine-Gordon yet. You can think about standard Galilean bosons. That is, of course, not a relativistic invariant. You need to work more to get sine-Gordon. Here I'm just depicting what the wannabe ground state of free fermions, but you can also think about strong interactive bosons will be. The ground state, all the particles want to stay at low momenta, but since you have Pauli principal exclusion, you start having a Fermi sea. This is the ground state. I already told you the sine-Gordon emerges in the low energy regime. So what you need to get to get to sine-Gordon is to start looking at the fluctuations and excitation around this ground state. This is the famous Latinger liquid or harmonic fluid approximations. This will not give me sine-Gordon right away, but it will be quite close to that. How does it work? I want to describe the low energy fluctuation of the state. So essentially, this comes from just shifting the position of the Fermi seas. Okay? I can do it either symmetrically, like in this case, and essentially this will couple to fluctuation of the density of the atoms. Just before, imagine that the Fermi sea is a bit larger here on the left and the right, you're going to just have more fermions to the game, but still with zero current. If you instead look at antisymmetric, if you want, shift the Fermi seas, I move both of them on the right, but to conserve the distance, I will retain the same number of fermions, but I will activate some currents. The average of the Fermi sea will not be placed at zero momentum any longer, but will have a finite momentum, and that is a current. And the Latinger liquid is nothing else than the harmonic approximation for density and current fluctuations. It is convenient to introduce these two operators by just telling me what the density fluctuations are, and it turns out that the current can be written as the gradient on some field. That actually turns out to be interpreted as a phase field. Okay? And here, it's just what you would write for an harmonic approximation. There is a term coupling to pi square and a term coupling to the current square. Here we're going to find some other parameters, C and K, that are tunable parameters. They are microscopic, that depends on the model under investigation. C, in the end, is the speed of velocity of sound or of light, and K is the Latinger parameter, that is connected to the compressibility of the gas. As you see, this is just resembling sine-Gordon, but it is not yet. This theory here, first of all, is non-interacting because it is quadratic, easy to solve if you want. It's also gapless because it doesn't have any, indeed, interaction that creates a mass term. To get sine-Gordon, we need to do something more and add another term here. And the idea is that instead of using just one-dimensional cloud, we can use two and couple them in a non-trivial manner. This is actually a sketch of an experiment done, here is the reference, is done in Vienna in group Jörg Schmidt-Meyer. He considers two quasi-condensate elongated tubes, but he can put them quite close together and allow, by tuning a tunneling barrier here, allow the particle to hop from one tube to another one. Okay, this will start triggering interactions in the model, and then sine-Gordon emerges as the low-energy field theory describing the symmetric degrees of freedom. What's going on here is that you're going to have a Latinger liquid for each of the two couple or the two tubes. Then, of course, I'm going to have two phases and two density fluctuations, but I can arrange them in such a way the symmetric degrees of freedom will still form a gapless Latinger liquid as before, that will decouple from the antisymmetric degrees of freedom. And the antisymmetric degrees of freedom will be now coupled through a tunneling term that is proportional to the cosine of the relative phase. And now, well, not surprising, but this is very nice. We get the wannabe sine-Gordon model we want to study. Now, the sound velocity and the interactions are fixed, if you want, by the background gas. Depends on the interaction and the density of the cloud. And instead, this amplitude here is fully tunable because you can just change in time, if you want, also the barrier between the two tubes. And this will affect the tunneling rate between one tube and the other one. So that you can study non-equilibrium, you can look at a lot of different physics. let me tell you something more about sine-Gordon, because of course it's a complicated field theory. I want to tell you something more about it later when we go in the quantum case. What are typical excitations in this field theory? Well, you realize immediately that this cosine term actually has a lot of degeneracies. Every time the field sits at 0 to pi integers, then you're going to have exactly the same energy. So in the landscape, potential landscape, you can have excitation that try to be around the minimum of the potential. This costs not much energy. Maybe you can have a hop to another minima, and then you keep on going with the same fluctuation. This theory here hosts topological excitations of phase winding in one direction or in the other one. I will call them kinks and anti-kinks. This, of course, you do not have if you kill the interaction term. These are not the only excitations. The kinks, anti-kinks are the only topological excitation, but on top of that, we have also bound state of data that are called breathers, and for which actually the mass law is known exactly on analytical grounds. So this is essentially the mass of the particles expressed in terms of the mass of the kinks. You see you have twice the mass of the kinks because it's a bound state of data, and then a function that lowers the energy. And these guys here are quantized in terms of n being an integer, where the argument of the sign goes from the minimum number you can have up to pi over 2. And you see that the Latinger parameter k, that is associated with the interaction in the tubes, enters critically in the mass law. And this will be very important for determining the quantum phase of this model. Now the question, is this implementation classical or quantum? Or maybe something in between. My claim is that it's pretty much classical, because the mass law essentially is determined by the Latinger parameter. And for weak interactions, as the current implementation done on atom chips here, 4K, that is essentially tells you the number of breathers, the different species you can have, is around 240. Essentially here, you see the mass law, the different mass of the breathers as normalized the mass of the kinks. And clearly, if you start seeing a continuum, you're going a classical limit. You are not able to distinguish the quantization of the particles any longer. And not surprisingly, if you sit down carefully, you're going to find out that here, the field theory can be actually well approximated by the classical counterpart. But of course, we would like to be here, having small number of possible breathers, and try to see if we can really engineer a quantum sine-Gordon model. So we need to have a strong interaction compared with the current implementations. How do we do that? Well, the interaction of atoms is more or less fixed, but in any case, what really matters is interaction against the kinetic energy. If you cannot really increase the interaction energy, what you can do is slowing down the particles in such a way that the potential energy, interaction energy is much larger than the kinetic one. And the idea is very simple. Rather than having an implementation on quasi-condensate, just try to build a ladder of a Bose-Hubbard model. These are just typical particles hopping around with some kinetic term, filling some on-site interaction, and we would like to have some tunneling between the two rungs of the ladder. Essentially, what is happening is here. We're going to have the interaction is fixed, but by tuning the lattice depth, you can suppress a lot the hopping term, and eventually the ratio between the interaction energy and the hopping potential gets very large, and you get the strong interacting regime of the Latinger liquid. This k equal to 1. This means that you expect 3 breathers. If k would be slightly larger than 1, we are around that ballpark. That is, of course, much less than 240. The first question we need to understand now, sorry, I was forgetting to say that since here we are on a lattice, now this guy here, it can also be simulated quite easily on tensor networks. This is much more convenient at dealing with a continuum field theory with a very large temperature. So what we want to do now, first of all, is try to understand if this approximation sine-Gordon is actually there. We know that eventually the model will be well described by sine-Gordon, but what is in practice the energy at which we're going to start seeing this field theory is yet to be understood. So now we start in theory land. We do tensor network simulation, not caring about the physical implementation and actual experiment, okay? Just to assess if the excitations are, if the coupled chain is very well described by sine-Gordon or not. Here what we are looking at is a spectral function of some observable that is really coupling to the emergent particle sine-Gordon. It's just the current across the rung that is coupled to antisymmetric degrees of freedom. Well, I didn't write it here, but of course, if I insert a resolution identity between the two operators I'm looking at, and I do the Fourier transform, I will sample the dispersion law of the emergent particles. Let me just remind you that sine-Gordon is a relativistic field theory, so we expect this kind of dispersion law, start parabolic and then goes up linearly in the momentum. And this is actually what you're going to see in the spin chain. So you start indeed parabolic, you go up. If it would be an exact description, this would go up like straight. Of course, it's not doing that. At large momenta and finite energy, you start seeing excitation that do not belong to sine-Gordon. But still, we have a wide region where sine-Gordon is quite well realized. According to the interaction we're using, we expect for breeders, we have them. The mass ratio is actually correct. They just the numerics again against the exact prediction showed before. Moreover, we can also understand the size of the peak that is actually a prediction of the field theory. So here you see tensor networks against exact analytical prediction. At a small momentum, small energy, everything fits. Of course, if you go to large momentum, you're going to start seeing corrections, but it's fine. These are just other different sampling for the mass and interactions. Everything works. We can also do much more. Of course, the particles are there. We see the mass with the dispersion law, but what really matters in field theories are the interactions. How do we prove interactions? Through scattering. We can look at a scattering event, and in generic system, we expect that whatever scattering is allowed by energy momentum conservation will be realized. But instead, this model is special. It belongs to a special class of models called integral models, where scattering needs to be elastic. Particle in, same particle out, even though energetic will be possible to couple to other particles. And the only thing that you're going to see in terms of interaction is a scattering shift after time of scattering. It's just a particle that will go on as if it was free, but then because interaction is instant scattering. This is actually a simulation that we did, creating two wave packets of two breeders, making them to collide. Of course, this is theory. It's not possible with the current knowledge in experiment, but theory-wise, we can do that. We make to scatter two particles in sine-Gordon. We see two straight lines without backscattering. We don't see a reflection of the particles. And moreover, the small scattering shift is actually in good agreement with field theory prediction that we can get from the exact solution, the sine-Gordon model. So we are quite happy to see that we have the right particles and they interact as we expect. So far was really theory land. I will not get to our actual experiment in the end, but I want to start bridging between the two. So before we are doing like things taking full advantage of numerical simulations and analytical calculation without caring about the possible implementing it in actual experiments. So our proposal now is to try to look at this field theory in a quantum gas microscope that can actually access the quantum regime of the field theory that we want to look at. But of course, now we have some constraints. We have some capabilities that we can do, what we are allowed to play with, essentially in situ projections, in situ projected measurements of the number of particles, and we can dynamically change the coupling of the Hamiltonian with local resolution. And what we would like to do is to be able to prepare the ground state, because we need to start at low temperature, try to put some excitation in a controlled manner. This is not an easy task, and finally to detect those excitations. The problem is that the sine-Gordon is not a microscopic theory, it's an emergent field theory. So whatever local operation you're trying to do, you will couple to the actual atoms and will project it outside of the effective sine-Gordon field theory. So you need to be very careful on what you are doing. Ground state preparation. Well, the model as a whole is gapless because there is a Luttinger mode, but that decouples from the antisymmetric degrees of freedom. This actually is gapped because sine-Gordon has a finite mass. So in this case, adiabatic state preparation works. You can start with a unity filling single well that all of them are decoupled. Something Maybe I can have extra 2 minutes because of that. So as I was saying, and then the slide will confirm that adiabatic state preparation works, and we can engineer with nice fidelity the ground state of the sine-Gordon model. Energy is not very informative because symmetric degrees of freedom get very highly excited, but we can access the quality by looking at spectral function that we were looking before. And here we have the true ground state against the adiabatic prepared one. Times for this to be prepared around 50 hopping times, so should be feasible. Next, there is a problem of imprinting particles. We want to imprint the phase some topological particles, and to do that we need to give some phase to the sine-Gordon model. This is not easy, but what we can do is take advantage that the current, if you want, can be associated with the phase. This is a way to detect what's going on, and try to excite some current by putting some imbalance in chemical potential between the two wells. The beginning are symmetric, now at tilt time particle will try to flow from one to another one. If you do so, of course, if you just keep on giving a kick, it could be that your kick is not good enough and you are not managing to pass from a value the potential to another one. Of course, if you kick it too much, you're gonna give it the particle, the phase, too much energy, and it will not just make a jump, but it will keep on traveling at different values in the potential. So the way to implement it is first to kick it, and then to suddenly, not to suddenly ramp it up the mass potential, in such a way that the phase gets trapped in the next barrier of the cosine interaction. This is what we did, and indeed we managed to excite solitons in a controlled manner. Here we see a phase pushing that in the end is engineered one soliton. The current before goes up, then goes down, reaches 0 again. And notice here the not excitation, that means that we are really close to create a not excited ground state both on the right and on the left, and the middle will be a soliton wave packet. And if you push more, of course, you can get 2 solitons as well. This is just a plot of the average current, is not a detection of the phase, and this is actually something that we would like to understand. As I was telling you, we just had the current. The current is non-topological. You just see a bump localized, but you don't understand if you just have a breather that is exciting some current locally, or if you really have a topological excitations. To see that, you should do something more. A possible idea would be just to try to recover the phase knowing the current, so doing measurements of the current and try to reconstruct the phase. But this doesn't work well, because of course the current is a macroscopic observable, while this phase is belonging to an emergent field theory. You need to coarse-grain to try to wash out microscopic degrees of freedom. So if you want to do local averaging. If you do that at the level of a current, you don't see anything. We tried that. Actually, thank you, Elizabeth, for that much efforts in this. We tried to measure the current. There's some quantized value. Essentially, either you see a particle or not. Try to do local averaging and see if we can recover the phase by fitting a phase profile there. This doesn't work because the soliton is small. If you do the calculation, you're going to find out that the size of the soliton where the phase is changing is actually a couple of sides long. So if you do local averaging, too small, you're going to see a lot of quantum fluctuation. Too large, you wash out the soliton and you do not see anything. So this doesn't work, you have to do something else. And the idea is try to find out an observable that does for you the job of doing a local averaging without having the problem extracting the phase from a nonlinear function, because the sine is a nonlinear function. If you want the local averaging or the function is not a function of the local averaging, and that is the problem. If you sit down, you can find, well, these are just some observables you can actually compute, and I will tell you how in a second. That is essentially the energy of particles hopping across the rung, the kinetic energy, and the current. Okay? And if you build out this weird combination of them, and there's a reason why I'm doing that, because we are looking at observables on different sides, so all of them are commuting, we can measure all of them at a different time. If you do the field theory calculation, you're going to find out that these are coupling to the derivative of the phase field. So we get the phase field through its derivative. If we integrate it out, or if you want the lattice summing, from the field theory point of view, this will start sampling through the phase feeder through position. We fix one, and we start sampling the other one, so we can recover the solitons. This is actually a very nice way to probe the phase, because it's a linear map of the microscopic degrees of freedom to the macroscopic one, so behaves well under local averaging. It's actually a summation, so it's already taken into account local averaging, because you are summing on many degrees of freedom, and you are washing out the microscopic fluctuations. Furthermore, this eventually will be a conserved charge of the sine-Gordon model, and this is important because if I want to look at some degrees of freedom, I want that measuring it, I should not change the state. And this is actually what's happening here. And this map here, this charge here, can be actually measured in a real-life experiment by doing beam splitter operation that can map the current and the energy in different number of atoms in each rung. So essentially, you prepare the state, you do your no-equilibrium process, then you alternatively apply these gates, you measure the density of particles, and eventually you get the range operator that you need to compute the phase. Just want to show some plots, and then I'm closing. These are the same current plots I showed you before, but now we can look at the phase and discover what we found out exactly what we were expecting. We're imprinting a soliton, and we can also imprint two solitons, of course. Here the size is not exactly this twice the first one, but just because more or less we imprint two solitons, but some of energy can be stolen by non-solitonic degrees of freedom, so by pushing, we are not pushing hard enough, if you want. Notice that at large times, here the plateau remains constant at different times, and this is non-trivial, because sine-Gordon has a mode that is topological, so it would be protected, topologically protected here. But from our point of view, just a summation of microscopic degrees of freedom, and there were no reason to expect a priori stability of that plateau. So these are other non-trivial confirmations that we did with sine-Gordon. I will conclude, otherwise Marikam will kill me. So the take-home message is that we can actually implement, is a promising venue to implement a quantum simulator of sine-Gordon field theory. Can be just found if we promote a coupled condensate implementation to a Bose-Hubbard ladder. This will allow us to access much stronger interactions, and eventually will end up in a stronger, strong interacting and truly quantum sine-Gordon field theory. Nicely, since we are not chain, we can use tensor network to access the few particle regime of the field theory. Of course, there remain out the question about looking at the really fine density excitation of the sine-Gordon field theory. That is why this implementation on the Bose-Hubbard ladder would be quite cool. I try to convince you, but of course time is not my friend here, that looking at quantum effects of the field theory makes things much more difficult than in an experiment close to the semiclassical limit. This holds both for implementing the excitation to measure them. And of course there is the big question if this theory, as much as careful we could be, there's still to be seen if it is realizable in actual experiments. We are hoping to see it in the future. I just want to thank the team. Actually, I was about to say that most of the authors of the paper are in the audience, but actually I see only Elizabeth down there. Then there is Monica, Emmanuel, and Mika Knapp, my advisor at TU. And well, thank you very much for bearing it with me.
Thank you very much for the nice talk. I have to ensure you that I didn't threaten Alvise at all.
Sorry?
I didn't threaten you physically, if you didn't.
Oh, I see like 5 minutes.
But now there is time for some questions.
Okay, all prepared.
Yes.
Thanks for the interesting talk. as you probably know, a large amount of work on sine-Gordon physics was done with fluxons in Josephson transmission lines. But these systems always have been described classically, taking the phase difference as a classical variable. Could your approach now give more insight into these experiments done with fluxons in Josephson junctions?
Well, of course there is a problem if the Josephson junctions are in a regime that is close to the classical limit or not. Okay? To my understanding, to what I've seen so far, they're pretty well described by classical physics. Okay? What we are trying to implement here is the field theory in a different regime that is truly deeply quantum. And of course, if it is possible to realize a different experiment with Josephson junction that is exploring the quantum regime, then this implementation will be highly tunable and can give insight into that. The question is, where are the experiments? If you want, if it is a matter of probing close to a classical point, maybe the current implementation with cold atoms is already good enough, because they are really deep into the classical regime. It depends where you are with the Lattinger parameter or the parameter that appears in the Josephson junction implementation.
Yeah, probably one has to change the ratio of charging energy to Josephson coupling energy in these strip line geometries to approach the quantum regime, but I do not know whether there have been experiments already done.
I've seen recently a theory paper that was going to that direction, but I do not know if it is really experimentally feasible. That I do not know. It would be really nice to discuss this.
So we can take one more question. If not, maybe, so in these scattering simulations, you were using already the discrete version.
Yeah. Like
so
here we really want to look at the physical model, the coupled spin chain or coupled Bose-Hubbard model, and imprint on top of that the field theory excitations.
So is it not an issue that you have too much energy to be
That's
close
the point.
to the...
That's also why I here stress that we are in theory land. So what we do is, first we excite the wave packets at low momentum by having a smooth, by applying a smooth version of a local operator. This selects for us small momenta, that is where sine-Gordon lives, but doesn't smooth out large energies. Okay? A possibility for doing that would be either try to be slow, that will filter out slow energy, but the problem is that the wave packet will start moving, and it's not nice. So what we did here is a trick. We applied, after having imprinted having applied the local operator, Euclidean time evolution to cool the system down artificially. So this why is not doable in experiment, but what we want to do is, if we have the web packets, if it is interacting as we expect.
Okay. Thank you very much. So I think we should move on. Let's thank Alvise again.